So today we'll be talking about forming timber and some principles related to that. What does it mean to form timber, to make something out of timber? There we go. A little bit about me. So I studied in the UK. I did my PhD at the University of Bath. But I don't, during my masters, my research masters, I studied timber grid shells, elastic timber grid shells in some detail, and I fell in love with that system. But during my PhD, I went a bit further in terms of mathematical and numerical modeling of the mechanics of thin, bendy things. It got quite mathematical, but still, I loved the principles of the active bending in general. I followed up by working for Bollinger Grohmann in Berlin, a structural engineering company, and AKT2 in London, also structural engineering, where I was involved in computational design, engineering per se, and the R&D agendas of the respective companies. And I'm now based in Athens, and I'm working from here as a freelancer doing a mix of things of computation, engineering, and teaching. So we're talking about forming, and I always like to begin with looking at the word. So the word form obviously has, you have a thousand synonyms you can apply. What comes to mind when you think about a form? Shape, configuration, formation, arrangement, appearance, design, silhouette, etc., etc. So it's a very defined noun, but it is also a verb. So this points to the duality of what this course in particular deals with, which is the process of by which you arrive at a certain shape and the shape itself. They come from the same place. They are integral one to each other. One can follow the other, or vice versa. And we've seen that through your presentation. Sometimes we talk about the shapes, sometimes we talk about the materials or the systems and how they a final design arises. But I like this duality between the noun and the verb. I like to point you to a very good book called On Growth and Form by Darcy Thompson. I think this came out in either 1907 or 1917. I'm not sure. I don't remember exactly. But you can imagine this was a time when scientific discovery was kind of booming as it is nowadays as well. But there were new instruments being developed. There were better microscopes, telescopes, photography, X-ray, all these new techniques which allowed people to investigate the natural world in a deeper way. I don't know if I can do that. Can I? Maybe Enrique will do it. Yeah, I cannot let anybody in. So yeah, the book On Growth and Form came at a time when all these discoveries were happening, and people were studying the natural world in deeper detail. And Darcy Thompson refers to the waves of the sea, the little ripples on the shore, the sweeping curve of the sandy bay as riddles of form that can be solved by reference to their antecedent phenomena in the material system of forces to which they belong. So what he means is that everything in nature has arisen due to some mechanical and material processes. And this book kind of illustrates that, illustrates it very well. It has a lot of very beautiful diagrams, drawings, quirky fish and conformal mapping. So people were trying to understand the shapes of things based on how their environment was pressuring them in one way or another. And it's just a very beautiful book. For example, here you have slow-mo photography of droplets, and people started being able to see how a droplet that falls in water, what the shapes that arise, how the fluid moves, and so on, and therefore how some various species of coral, they must be, I guess, develop. Very, very good book. A modern equivalent to this is The Architecture of Emergence by Michael Weinstock, where unfortunately there's not so many pictures, but it's a similar philosophical treatise that to study form is to study change. And he talks about all the forms of the world as being energy and material systems that have a lifespan, exist as part of their environment, and they iterate through evolutionary development. He brings together energy, information, and material as a kind of a higher level exploration of what Darcy Thompson was doing. So these are very good books when you want to think about the process of forming the natural world. So let's talk a little bit about timber. Of course, is part of the natural world. It grows naturally. We have the trees which we cut down, and it's a great source of material for the structural industry, for the building industry. And there's a lot of intelligence within timber as a material. You've probably seen diagrams like this before, showcasing the complexity. So within a tree trunk, we have the heartwood and the sapwood. So the heartwood in the middle is darker, and I believe it's pretty much kind of dead material. It's inactive. There's nothing flowing through it anymore, and the sapwood is the growing part of the tree. And when you look at the different the process by which the trees grow, you get this radial display of the rings, and when you take different cuts of timber, you have different effects, different structural properties, uh, yeah, different variability. So this is a tangential surface, which looks like this, has a different aspect than the radial or the plain cut surface. Now, on top of the natural order of things, we come along and we chop down the trees to make construction materials. And there's a lot of intelligence and knowledge that goes into how you cut the timber, the different cuts, which gives you give you different properties, different moisture retention or the lack of that. And ultimately, you end up with a material which is orthotropic. So we have different Young's modulus, stress capacities, strains in the different directions of the timber. Primarily, we're talking the longitudinal and then across the grain, either radially or tangentially, depending on the surface. So a lot of variability and a lot of knowledge in thinking about building with timber. And then the next addition is the manufacturing of timber engineered products. So you have starting from the simple sawn solid timber, then we have different types of joists. We have glued laminated timber, CLT, nail laminated timber. You have the cassette type systems. You have hybrid systems with timber and steel. So you can see the variability is quite immense, and you should be aware of this when you choose any design solution for a project that you're working on, that there is this variability available, which makes you can make your design much more interesting, much more efficient, much more beautiful. So what do we want to form out of our timber? I like this sketch a lot. This is by Heinz Isler, a famous Swiss structural engineer, famous for his concrete shells. I think it's either in one of his books, he kind of ended it with this sketch showing the potential for for concrete shells, and the key is the etc. here at the end. So you have all of these things, etc., etc. So, and the possibilities are infinite. So what do we want to form out of timber? Well, not something like this, I guess, even though this has a lot of intelligence and complexity. I certainly wouldn't be able to build this in a very short time. But I guess we are looking more at something like this. And this is, I love this because it's a very inspirational image of what previous alumni have done in your shoes, and the possibilities of timber construction in the world of shells and grid shells. So we want to do something like this shell or a grid shell type thing. Then we need to understand what those are and how they work, right? So grid shells are doubly curved surfaces where the material is discretized in certain areas of the surface, and the material can be timber, obviously, but then there's other options, as you have seen, no doubt, steel, fiber reinforced polymers, aluminium, etc. But the grid shell is kind of a subset of a larger category called shells, which are doubly curved structures made out of solid material, so continuous material, typically concrete or rammed earth, masonry. We've seen today also with some panelation, timber also possible. As I said, shells are a structure or a structural element defined by a curved surface. And one of their key properties is that they are thin in the direction perpendicular to the surface, and their curvature is what drives their load-bearing capacity. So here at the bottom, we can see the Sydney Opera House, the real deal, not some AI-generated version, which is a shell structure roughly based on these doubly curved surfaces. So in order to understand how they work, you need to think that they carry the loads primarily through in-plane axial stresses and in-plane shear stresses. So in-plane axially in the two orthogonal direction, and then shear stresses. There's also bending, but we want to kind of minimize that as much as possible, so that they don't act as beams, but they act as an eggshell itself. And the loads that we apply, be they gravity or wind or all other types of pressure, they are balanced by the membrane stresses and the curvature of the surface that they are based on. So therefore, if we go back, we want to form something out of timber that's a shell or a grid shell. The way they work is they need their curvature, therefore we need to understand curvature a little bit. This is a little article I found in Nature about how two-dimensional bending can extraordinarily stiffen thin sheets. This is an experiment you can do probably in the next 30 seconds. If you take a piece of paper and you just cantilever it out, it will just flop downwards. It will not be stable at all. However, if you impart it a little bit of curvature in one direction as you hold it with your hand, you will see that it's able to carry its own weight and cantilever out, and it could even carry a small object like a little pin or a light pen or something. So this is a very good example of the power of curvature and how it helps shells carry their loads. Yeah, so in order to understand curvature, I have a series of slides kind of going through the different types of curvature and trying to simplify their understanding, hopefully as much as possible. So, excuse me. We've decided we have a curved surface that we want to design. We want to build our timber structure into. So we need to understand surfaces and curvature. Surfaces are two-dimensional objects which are embedded in our three-dimensional space, and usually we have a two parameter parametrization on the surface, giving us two principal directions. And say we put a curve which follows our surface to a certain degree. This could be, our timber grid. So let's look at that curve. That curve can help us define a number of different types of curvature. Firstly, normal curvature is curvature that on that point on the surface is defined in the plane tangent to the curve and normal to the surface. And the curvature, obviously being the inverse of the radius, can give us this circle of curvature. So this is normal curvature in the plane tangent to the curve and normal perpendicular to the surface. Then we have geodesic curvature, which is in the plane tangent to the surface at that point, and it is aligned with the tangent of the curve, and it gives us the geodesic curvature. So how much this red curve is bent kind of sideways, if you can imagine. So we have the normal curvature and the geodesic curvature. The geodesic curvature is important. For example, here I'm showing in yellow a curve which has the same start and end point as the red one, but it is what we call a geodesic curve on that surface. And that means its geodesic curvature is 0. It just has normal curvature. And that's what we see kind of represented here. It has a normal curvature value, but the geodesic curvature is tends to 0. It is 0 in pure mathematical form, which means the radius is infinite, right? So this circle is infinitely big. And that is important for us because we understand that the material we put on the red curve will have to bend in two directions. So we need to account for that. So we have two. We have normal and geodesic curvature. Then we come with the principal curvatures. Now, if you imagine the tangent plane on the point on the surface, there's pretty much an infinity of directions in which you can check for the curvature. You can just rotate around that plane and see what the curvature is on the surface. And therefore, there's a spectrum with the smallest and largest value. And those two are the principal curvature. So here, the smallest one is, highest curvature, lowest radius is the principal curvature 1. And then the other one is this one, which is much flatter. So those are the two extremes on that point. And together they give us a, fifth measure of curvature, which is Gaussian curvature. It being simply the product of the two. And what I'm showing here is that, yes, so the principal curvature is the smallest, one of them is the smallest value. So the normal curvature here shown previously it's in another direction, and it is smaller than the principal. It is bigger than the principal curvature. The Gaussian curvature is very important because the product of the two of them can be positive, negative, or 0, and this tells us different things about the surface. So if the product is positive, you have a dome type surface. If the product is negative, you have a saddle type surface. And if the product is 0, you have a developable surface, which is like a cylinder or a cone, which is very important for practical purposes because it can be unrolled and laid out flat, or thinking in the other direction from the process point of view, some flat sheet of material can be bent into this curved surface. We also have mean curvature, which is simply the average of the two. On this particular example, the mean curvature h just has some values. It's nothing important. Where it does give us some insight is when we talk about minimal surfaces. These are surfaces made by soap film on arbitrary edge boundary curves. So these are the surfaces with the least area which can fit on that boundary, and they have a mean curvature of 0. Returning a little bit to the principal curvatures, as we said before, we have the two directions of the principal curvatures being the highest and the lowest curvatures. And as you walk along those directions, you are pretty much, if you imagine yourself shrunk down on the surface, you are pretty much not swaying to the left or to the right. You're just leaning forwards or backwards, right? But there's another thing that can happen, which is as you walk along a surface, you can twist. Your body can start to lean left or right. So twist is also an important quantity to be aware of, which I will try to illustrate in the next couple of slides. So let's go back. We want to design a structure for a surface of a given geometry. We then put our a curve on that surface, which is where our material would be, timber in this case. And then we're looking at that curve's properties. So we have a frame of vectors we can define. The first one being the tangent of the curve. The second one being the normal of the curve, not of the surface of the curve, but the curve lives on the surface. And the third one being the binormal, which is just the cross product of these two. So you have an XYZ type frame. And if you plot that along the whole curve, you'll find that there is an amount of twisting around the tangent. You can see in the green area particularly well. So the twist is the change of the normal and the binormal plane around the tangent as we move along the curve. Now, why is this important? This is important because we need to know how much our timber can twist in order to match the surface design we want. So again, imagine putting your timber planks on the surface and it needing to do some kind of twisting like this. You need to be aware of that in order to account for it, to design for it, to check for it. So that wraps it up. We have the normal curvature, the geodesic, the two principal ones, the Gaussian one, the mean one, and then the twist. So that's quite a lot of quantities that are relatively important, and that's why I wanted to briefly showcase them so that you're aware of what can happen on a surface. Going back to grid shells, so we have I would classify them in kind of two types. Firstly, we have elastic grid shells, which are bent into place, bent into shape, and they are typically formed of long continuous elements overlapping each other in different directions, and then a rigid elements, which are a bit easier, but they are shorter. There's more connections, and yeah, it's a different type of construction and behavior, but same overall effect ultimately of building a grid shell. So today I will focus a little bit more on the elastic side of things. So in terms of that, the big idea for timber grid shell actually started in 1675 with Robert Hooke, who proclaimed that as hangs the flexible line, so but inverted will stand the rigid arch. So this is the famous catenary hanging chain methodology, where you hang a chain, you freeze the shape, flip it over, and it's an arching compression. But this is a very it's a very true principle, but it's only optimized for self weight only. So this is kind of true only for the self weight. And then the next big leap came from Otto, an architect in the 60s and 70s. He latched onto these ideas and kind of spurred the whole evolution of these types of structures. And firstly, we had the Essen grid shell, which was this relatively small pavilion. Basically, Fry Otto took Robert Hooke's idea for the chain and made it 2D. So he said, what if you have a flexible mesh net which you hang, and then if you flip upside down, you get a shell shape which is in compression. But in order to achieve that, he kind of took it literally, having the mesh. So you have this grid of timber which can rotate with respect to each other. So everything starts out as squares, but in the hanging or respectively fully constructed dome, you create these diamonds and you are able to modify the grid and to map it to this surface. So this was the big idea. Some advantages. So it was a flat assembly, which was then lifted in place, as you can see by the crane. It's got repeatable nodal connections, all of them the same. Makes it cheaper and easier to build. Very simple fabrication and a relatively simple construction. And at the time, they were doing physical modeling to do both the form finding, as I said, hanging mesh, hanging chain, and for the load testing. And to me, this kind of culminated a decade and a half later, almost, with the Manheim Multihale, which was this great exhibition space with two large domes and interconnected tunnels, which took the same principles from that prototype I showed you, but just took it to the next level and innovated in a number of different ways. We will get to this a little bit later, but first I will just give you a bit of the timber grid shell fundamentals, or the elastic timber grid shell fundamentals. As I said earlier, it being a shell, it transfers the loads mainly through axial membrane stresses and membrane shear stresses. We try to minimize the bending out of the plane to make it work as an eggshell. Now, when you have a grid, then that has to happen by having multiple directions to account for that, and adding the bracing. But the force transfer, the force behavior has to ultimately be relatively the same between a shell and a grid shell. Second big component is the layering. So you can have a single layer with one layer in each direction, or double layer when you start to stack up, and then more and more and more. There were the famous Natterer systems where or some of the Japanese designs where very thin strips are added and you have 6, 7, 8 thin layers on top of each other. So yes, forces transferring in double directions, plus the third, and the layering, very important. Then we have the bending, so we need to be aware of the surface and therefore the curvatures, because those curvatures induce bending into our timber, and we need to know that there is capacity for that bending and it won't break. So using the simple bending equations, you can get a pretty rough estimate of so the stress in the material being a function of Young's modulus, the height of the section, and the radius of curvature. And we need to keep that to, if we're working with Eurocode, to a fraction of its allowed permissible stress of the material, which is derived from the characteristic stress of the material plus safety factors, in this case in EC5. But I say a fraction because we also want to leave room in the section for stresses caused by external loads. So not take everything to 100% capacity in bending and then a strong gust of wind comes and there's no more capacity to take extra loads. And yeah, here I'm just showing the section, so the rest of the equation from down here. Another important aspect is the composite action between the layers. So once you start to layer up, in this case with quite square elements, it's good to ensure that the two layers are working together. So you often add a shear block here, which mobilizes both of them to work compositely as one section. Whereas if you don't do that, the length from node to node, they are just working individually. So it's always a good idea to do this. If you have much thinner elements, then they can overlap each other, but you still add something to achieve this. I think last year's MPDA example showed this. I don't know if it's still up there and standing, but yes. Finally, no, not finally. Following, we have the connections. So these are some connection types which were used in the big projects. Firstly, for Manheim, there was a simple bolt through all the elements. Then later on, something like this was developed so that the bolt doesn't eat part of the timber section here. So the section is preserved intact. And all of them are pressed together using friction. They are locked into place. And there's some variation which you can add to that. You can add another layer for bracing. You can add another coupler or another mechanical fixing for something like glazing. So this is a system that has other advantages as well. And bracing is very important. So in this case, we use the natural weakness of the timber, the elasticity, to make a flat grid. We push it up into shape, but then we need to lock that shape, and the way to do that is to add the a third layer of bracing. So my options here are, making the node rigid, which is very hard in this kind of situation, just making a very fixed connection because the timber sections are small. Timber is difficult to achieve rigidity in timber connections anyway, so this is just as a philosophical point. You can have a network of tension cables. You can have a network of rigid timber elements which triangulate some of the quads, or you can have a membrane action using the whatever cover that is there to provide the bracing. Construction, another very important topic. So the first method we saw for the Essen was the lift up. So just come with a crane, lift the grid up, pull the supports, fix them, job done. Then we have the push up. So you push from below and then you pull the supports in. Another way to do it is to assemble everything at a higher level on scaffolding and then slowly remove scaffolding in a controlled way. And use gravity to help you, but you still have to control the final position of the supports. And lastly, there's also the option to inflate the cushion within a with underneath the net, the grid, and use the inflated cushion to give you the height and the curvature, and then pull the supports down. This can vary obviously across the scales, across the different projects, and the requirements. And finally, I think on this one is the buckling. So buckling is very important in all the compression structures, uh, and it happens in all elements subject to compression. So for example, in 1D elements, columns, they buckle out of plane if the axial force exceeds a certain value. It happens to arches, so you get these kind of buckled shapes. It happens to cylindrical shells, so surface elements, and this shows us two aspects of it which are interesting. So one, you have the global buckling, where this this tube acts as a column and it all goes sideways, and then you have local buckling, which is within the surface itself. There are localized effects. This is crushing your Coke can in your hand or under your foot type situation. And grid shells are subject to all of the above, really. So in this model, we see a kind of global effect of buckling where a large part of the surface is deforming. In this one, we see more localized effects similar to this, um, where just locally in the surface there's some buckling, and then also individually each element itself can buckle at some point. So there's a lot of buckling checks to be done when working with in grid shells. So I think that kind of covers the fundamentals. I will talk a little bit about some of the elastic grid shell projects. Firstly, Manheim Multihale, built in 1975 by Fraiotto with Arup engineers from the UK. I'm going to show some nice details. So this was a very interesting project. I think it was very courageous, very bold at the time, and there was a lot of innovation that had to happen on all levels. But at the same time, it's quite simple in a way, because if you look at the carpentry details, there's pretty standard stuff. Okay, here in this one, in the bolt that connects all the grids together, you have a little bit of a spring washer so that it gets tightened and applies pressure, which applies friction on the interface between the directions. But the other details, they don't look massively complicated. We have the third layer of cables which brace the structure. In this case, they had every six grids there was a crossing diagonal going through. And oh yes, so here there were splice joints. So in order for these very long lines to be continuous out of timber, they introduced splice joints, which you can see kind of provide a little bit of rigidity, and it's not as smooth as if it was a whole continuous element, but quite hard to make a 80 or 100-meter long timber element. Another thing I really like is the variety of boundary conditions. So this diagram shows that they had 4 types of boundary conditions. They had a simple concrete boundary. They had some arches for the entrances. They had laminated timber beams up at a higher level, and then also a cable boundary, which we'll see shortly. So this is the arch boundary where the grid was kind of sandwiched in between these panels and this edge beam. And the cable boundary is a tension-based system, almost like an inverted truss, which would receive the grid at this level, and then there was some counterbalancing tension on this side. Very bold for this, very bold. Now this was built and it was supposed to be up for 2 years. It's been up since 1975. There's a lot of damage that's occurred to it. These are photos that I was able to take myself a few years ago when I was able to visit it. So there was some buckling that happened in the main dome. You can see the dimple here as it buckled inwards. That's why the support tower is there. Here it looks like there's a lot of repairs and damage, damage and repairs subsequently with these splice joints. I don't know if these were pre-planned. They don't look like that. There's some damage at some of the edges. For example, here the grid is completely destroyed and the cables don't look in very good shape. And here there's some additional support needed for some of the edges. This had been closed to the public when I went there. And there is some good news. I do believe that there is an effort to restore it to some degree and to preserve its to preserve it. It has been recognized of great value by Germany and by the state in Mannheim, and I believe there is an effort in progress trying to give it back some life, and hopefully they will succeed in that. A few more projects. So then we have the Weldon Download Open Air Museum, which is a very beautiful hourglass shaped grid shell. I'm going to focus on the kind of the innovations that each project brought. So in this case, they introduced bracing by diagonal timbers as one of the options I showed you in the beginning. But you see on the sides, they are placed horizontally, and over the top, they are placed transversely. And that's just because at the top, they want to have some lighting coming through, and at the sides, they wanted to clad it. So this matched the architectural intention quite well. And another interesting feature is the density of the grid, going from 1 meter grid to 0.5 meter grids. So there's some variety there due to the structural requirements following the structural analysis, I think. It's a beautiful space. It's used for restoring old timber buildings, actually, in the UK. And here's the detail I showed earlier, where the two grids are captured in one node, plus the bracing, which runs horizontally behind, onto which the cladding is then attached. So here you see, thinking about the systems of everything coming together, that's how you make a great design product. Savile Garden grid shell. This was 3 years later, and pretty much built by the same team as the previous, as Weldon Download. The main innovation here was the lifting up of the whole grid onto a steel edge beam. So this is purely a roof floating nicely over the entrance to the Savile Garden complex. And in this case, it was built high up on the scaffolding and then lowered down. You can see here the first two layers plus the shear blocks. Here the shear blocks are twice the height of the element itself, so you get a bigger depth overall to the system. So that's one of the innovations that came through on this project. And yes, so firstly, only the first layer was brought down, and the second layer was applied onto the curved surface. So the sequence was build the edge, layer 1, then the shear blocks, and then layer 2 on top of this. And finally, here membrane bracing was used. So the plywood that covered all this was used as the bracing system. So no cables or diagonal members, just plywood on top. This is a small pavilion that I was involved in almost 10 years ago. We did a very early simulation type thing where it was a pavilion going to be built by students. So we knew we wouldn't have access to a lot of equipment, a lot of cranes, things like that. So we said it's probably going to be a bunch of us sitting under it and pushing upwards and pulling the supports to the location. So let's integrate that into the form finding process. We have this grid, we have those actions which simulate the construction, and we will have this shape at the end. Yeah, so this was the simulation that we did for that, using Kangaroo as well back then.
Kangaroo 1.
Kangaroo 1. And this was the built system. Unfortunately, you can see it's quite flat. We weren't able to push to the required height and to pull to the required support position, which meant that this was quite flat in the end and not as efficient as we had designed. But it was temporary, so it was okay. But it was a good lesson in failure. And finally, there's a project I worked on while I was with AKT as a luxury development in the Red Sea in Saudi Arabia, where this hospitality entrance for some hotels, some villas, are to feature these two big grid shell type domes. So here we had a different case where the form finding was not there. We had a given surface and we had a lot of work to do to try to fit a timber grid on it that could work as an elastic grid shell. So you see here we're proposing the two directions plus the diagonal cables. A lot of studies of curvature, a lot of studies of curvature to try to find something that works for this shape. But this can be done, within Grasshopper with all the plugins. You can do form finding, stress checks, stress calculations, visualizations, everything all in one go. Here we're talking about the forming stresses due to the bending itself, plus the active stresses due to the loads. So we always have to combine those and check. But you can kind of do this within Grasshopper plus all its cousins. And this is a picture of it deforming under its own weight. But yeah, then you can go into BIM, you can go to inside Revit, and so on and so forth, and fabrication drawings. So from Essen to this, a lot of technology has come about, but the principles are pretty much the same. And the truer you get to those principles, to the material, to the system, to the forming, the better the design will be, I think. Thank you.
Thank you very much, Dragos.
Thank you.
So, guys, if you have any question.
Any questions?
Did they build the grid shell in the Red Sea, on the Red Sea?
I think it's in the process, yeah. It will be coming up soon. I had someone who was visiting the manufacturer for another project, and he said he saw the he saw the laths there, but they had to be pre-bent, unfortunately. So because of the geometry, they had to be split I split them in 4, I think 3 or 4 thinner slices glued together and preformed. So quite a lot of nastiness.
Thanks.
Anything else? Was the curvature part clear? I mean, that's the thing that you'll might use the most from. Hopefully that was clear enough. The other stuff is for inspirational purposes and motivation.
Okay, then thank you very much to all of you, and let's see next week.
I think I will see you in 2, right?
Yeah.
In 2 weeks. Yeah.
Okay.
Thanks, everyone.
All the best.
Thank you.
Bye bye.